Hello, everybody. Thank you for joining this conference. This presentation is about high-performance SMR drive with DIMM zones. All of you might be aware about SMR drives, which have been around for quite some time now. And there have been several presentations at this and earlier conferences about SMR drives and the capacities and restrictions of them. Most notably, SMR drives have two types of zones. One is random access, where the zones behave just like normal disk drives and can access randomly as normally. And the other type of zone is sequential write, which can be accessed for reads, just like normal zones with random access and everything. But for writes, they will only accept writes in a sequential matter, meaning starting after a so-called write pointer. The typical characteristic of these drives is that the number of sequential write zones are substantially higher than the number of random access zones. The problem with that one is that regular file systems assume random access devices, and as such, there are some modification required to make regular file system to work natively on SMR drives. These modifications take a long time to be deployed in the field, as file systems tends to be one of the most persistent types you can find in an operating system. So, to ease up this one, Western Digital developed a device module called DIMM Zoned. The overall design idea is that one can use the random access zone to cache the data. So normal I/O will just go into the random access zones, will be assembled there, and once the zone is full or need to be moved out, they will be copied over to a sequential write zone. As the copy is a single step, it is quite easy to observe the sequential write restriction, and the data can be moved freely to any zone. For that to work, there is an internal remapping between the actual data, the logical LBA number, and the zones, such that internally any LBA can land in any zone. To give you a bit of an overview about the operation, I did a brief sketch here how the thing does look like. On the top, you see the logical on blocks, where each block corresponds to an LBA. So if we now start with writing to LBA 0 on the very first block, here marked in red, you'll see that first we mark the first zone in the translation table as used, and then set a reference to the underlying random access zone and copy the block 0 on into that first random access zone. If we now write on another block into the very same zone, we don't need to change the mapping as it's the same zone, and we can just copy the block to the mapped random access zone. If we start writing to another block, this time in another zone, we first again need to set the pointer in the mapping table, set the mapping to another random access zone, and copy the data into the random access zone. And now we start writing to yet another zone. What we see here now is that we run out of random access zones. So we cannot simply write the data into random access zones because there are none. So we have to do something, which means we will have to copy out data from the random access zones to clear up data there, such that we can write the new data into the random access zone. So we start copying the data from the oldest zone into the sequential write zone, update the pointer in the mapping table, and then we can start writing the new data into the then free random access zone. And of course, as you can see, we do need to update the mapping table too, such that it will now point to the first random access zone. If the system is idle, we can start moving out data, such that moving out data meaning moving data from random access zones into sequential write zones, such that the random access zones will become free and will be ready for use for the next I/O operation. This works just like the earlier operation. We copy out data from the random access zones to the sequential write zones, update the pointer, and have a free zone. And then we can start with the other random access zone, copy out data, update the mapping pointer, and again, and hence all the random access zones are empty now. We can control this operation with two watermarks. The one is the high watermark, which signals if the reclaim, meaning moving out data from random access zones, should start. But as we still have enough random access zones, there is no need for it to run it at full speed, so we can throttle it, and it will be interrupted once there's real I/O coming in, such as not to interrupt the I/O flow. With the low water mark, it means that the reclaim should start even if the system is under I/O. And of course, we should remove the throttle such that we can clear out I/O as fast as possible. The problem with this approach is that the performance of that method, of the whole system, is being dragged down. The problem, namely, is that random access zones have lower performance than sequential write zones. The reason for this is typically because accessing or implementing random access zones in an SMR drive requires a high overhead of in the drive itself, as it basically has to emulate normal random access behavior on top of SMR drives, which drags down the performance. And also, the other problem is that we're having a degraded disk performance during copy zones, as we have to copy zones from one zone to another, which means that we have to copy the data from the disk to the OS and then copy back, thereby limiting the bandwidth for the entire disk and hence dragging down performance. While DIMM zone works nicely and gives a consistent performance, the overall performance isn't that great. And I've also looked at the setup and found that it should be reasonably easy to scale DIMM zones, both in capacity and in performance. The design idea for this are that random zones do really act like a cache. And as such, there's no real need for them to be on the same disk. So we could add a separate device for holding random zones or containing just of random zones. The second observation is that the sequential write zones are arranged in a linear fashion. So it should be possible to just concatenate several SMR drives to form a large logical drive. Thankfully, Device Mapper already provides for the infrastructure of such a setup. And the zone mapping and the mapping, which Device Mapper provides, can direct I/O to unused disk. So it should be possible to increase performance by always directing I/O to those disks which are not used or least used. The other nice thing by separating out the cache onto a separate drive is that we can use a fast device for cache like an NVMe or an NVDIMM to increase the burst performance, meaning for any I/O which just goes into the cache. And that should scale reasonably well, as all disks are independent, and so we should have a combined bandwidth of all disks in an ideal case. For the implementation, I had to update the on-disk metadata such that it can handle several devices. And this update meant that I had to separate out the different types of metadata. Originally, DIMM zones had two sets of metadata at the top of the start of the disk, the primary and the secondary metadata. This was done primarily to insulate against any sudden power loss, and such that we always are guaranteed to have a consistent set of metadata on the drive. If we were to duplicate this setup on all drives, performance would go down, as we would have to frequently update the metadata on all drives. To be precise, we would have to update all metadata on all drives for every I/O, which is not going to scale and really drags down performance. So what the approach we took was to introduce tertiary metadata to be stored on the SMR drives and keep the actual I/O metadata only on the cache device, such that the cache device has the primary and secondary metadata as in the original design, but the SMR drives would only carry tertiary metadata, which are just used for assembling, for the initial assembly of the overall setup. After that, that metadata isn't updated anymore and will continue to stay on that drive. For normal I/O, only the primary and secondary metadata is updated. And if we're using normal drives as a cache device, of course, we do have the problem that these devices don't have zones as such, but it's quite easy to emulate these zones by just setting a virtual layer of zones on top of the regular drives, where each zone has the same size than the zones on the normal on the other SMR drives. So the resulting layout is something like this. So on the first, you see the cache device holding the cache zones and also the mapping table. In fact, the mapping table is also stored on disks, so just before the cache zones. And then we have the first and the second SMR drives containing of random access zones and sequential write zones. And all of them are arranged in a linear fashion, such that we have a linear layout, a linear logical layout containing of all the zones on all drives. In testing this, I ran into several issues. The biggest problem I found is that SMR support on RAID HBAs is very limited. The standard RAID drives, Broadcom RAID HBAs, do not have support for SMR drives. The microchip RAID has some support, but it turned out that there was an issue with the implementation, making it essentially unusable to do real testing. So I had to resort to use the normal SAS HBA, of which there only is the sole remaining, Broadcom is the sole remaining vendor, and to connect my drives. The other problem I had was that a standard 2U server can fit up to 3.5 inch disks. There simply is not more space in the front shelf to put in drives. So if one wants to have a higher disk count, one would need to have a dedicated enclosure. But if one has a dedicated enclosure, this enclosure would need to be connected. So that there might be a limitation due to the enclosure connection, which typically runs on SAS, which is either 6 gig or 12 gig SAS. In my case, it was a 6 gig enclosure because that was the one which I found in our storage, in our server room. And I used a 20-core dual socket Intercion with 128 gigs of RAM and 265 gig NVDIMM as a cache. I used the Broadcom SAS 9300 as a SAS HBA, which is connected to a JBoard via a 6 gig SAS backend. Into this, I put 12 Western Digital 40 terabyte SMR drives to serve as a test bed for this presentation. So, and then I did a performance test using FIO with normal read and writes, and scaling up with the number of disks. By using 2 disks, we do see here that after a certain cutover point, so after about 110 rounds of testing, the number of free sounds went down to 0, and then the performance dropped to the raw disk performance, as we would expect things to happen. With 4 disks, the pattern is roughly similar. So the number of sounds goes down, while there are a number of while we do have free sounds, the performance is pretty good at around 2.6 gigabyte per second. But after we use up all free zones, the performance drops and we get the raw disk performance. So again, it's looking pretty good and just as we would have expected. When using 6 disks, the pattern is slightly different in the sense that the performance is exhibiting a higher fluctuation. So it's you do see quite some fluctuation both at the cache layer, both in the caching behavior, but also on the disk behavior. And also what one can see that between 60 and after 60 and before 80 rounds of testing, there is a bit of a plateau in the number of free zones, but the number of free zones is being kept constant. This is the low water mark of the zone handling mechanism kicking in, which is trying to keep the number of free zones at around 30%, which was set as a parameter at the start of these tests. But overall, the performance is still pretty good. We are still having the in-cache performance of around 2.5 gigabytes per second, and the disk-bound performance is at about 1 gigabyte per second. Still pretty good, and actually what one could expect in this setup. If we're having 8 disks, we see the same behavior than we've already seen on 6 disks. So the fluctuation is still increasing. The overall performance is slightly down from 6 disks. We do see a larger plateau where the low watermark is kicking in and trying to keep the number of sequential of freeze, or the ratio of freeze zones at around 30%. And due to that, the drop off in performance, which is happening as when there are no free zones available, is being moved out to beyond around 160. So we're having a far larger range during which we have free zones available. And with 10 disks, we again see a similar performance. The overall performance is slightly down again. We do see a higher fluctuation still, and we do see a larger area during which the low watermark is efficient, and the reclaim can keep on holding the ratio at around 30% free zones. With drought disk, it's even more marked that the fluctuation, even for the cache performance, is quite high. And again, the plateau is being extended to well beyond 106, around 106 60. And again, the overall cache performance is still down, so we are now with the cache performance of around, well, 2.2 gigabytes per second. So overall, we do see a quite good cache performance of around 2.5, or depending on the scale, 2 gigabyte per second. And there is, as expected, a drop in performance once all cache zones are in use. The performance drop is less noticeable with the number of disks, as the raw disk performance is getting up. But if we're using more disks, we do incur a higher performance fluctuation. And here is a slide where I combined the previous outputs to get a better understanding about the scalability effects of this setup. As we see, the more disks we use, the more the cutoff is being moved out, i.e. the cache zone usage is becoming more efficient as we're having more time or more rounds during which we have free zones. But we also see that the fluctuation is increasing with the number of disks. And we also see that the raw disk performance in the happening after the cutoff is also increasing with more or less with the number of disks. Here here's a short an overview of the cache scalability. As I've already said in previous slides, that the raw cache performance is going slightly down with the number of disks, and the fluctuation is getting up. And here's a graph detailing out precisely this. So you see for the raw cache performance, the bandwidth is going down slightly from 2.6 gigabytes per second down to 2.4 gigabytes per second. And the error bars here increase, meaning that the fluctuation of the bandwidth is increasing too. So for the scalability, for the raw cache scalability, there is a slight performance degradation, which increases with the number of disks. And this might be due to an interaction with the reclaim mechanism, because even when we are operating just out of the cache, the reclaim mechanism is still being started to figure out if there's anything to be done. So, and which means that the more disks we have, the more reclaim workers we have. And so this might lead to the observed performance degradation, as that the system would need to check more reclaim workers for each test. But still, we do have a very good cache, a very good scalability. When we are in reclaim, meaning when we run out of free zones and the reclaim needs to start writing out data, we have found that there is a plateau during which the reclaim low water mark is being most efficient and is able to keep the ratio at around 30%. And this here now is a graph for this plateau, where I marked down the size of each plateau with the number of disks. So so you see here that with the number of disks, this plateau is getting larger and larger, and effectively means that reclaim is becoming more efficient with the number of disks, which again is a very nice observation, because it means, okay, we actually do scale, and the system benefits from having more disks as reclaim is working more efficiently, which just goes to show that our initial design idea, that by having more disks, we would be able to direct I/O to unused disks, is actually holding true, because that's just showing here, the more disks we have, the more efficient the reclaim becomes. So as a conclusion here, reclaim is again scaling with the number of disks, and it starts earlier. reclaim itself will be starting earlier with a higher number of disks, and it will have a longer period at the low water marks with the number of higher disks, which essentially means that reclaim becomes more aggressive with the higher number of disks. On high disk counts, we have seen that the drop in performance doesn't really show up on the slides anymore. But we've also seen that for 12 disks, not all cache zones have been used, which does indicate that we simply haven't tested long enough to observe the drop, because eventually the number of free zones will drop to 0. And what we really wanted here was to test, right, well, how does the system behave after all zones have been used up? Which means we would need to do a retest here with a large number of runs to get comparable results and to figure out how the system behaves in the long run with a large number of disk counts. And this is the graph we have, which again is quite similar to what we've seen on the previous slides. So we have a performance regression in cache-only zones. We do have a quite high fluctuation in both in the cache performance, but also in the disk performance. We do see again a plateau of during which a reclaim is running at low watermarks, and we do see a drop in performance after we've used up all disks. What is surprising here is that the raw disk performance doesn't go up as we would expect, but rather have a pretty steep drop in the performance, which then goes up again and is leading to quite some high performance fluctuation on raw disk performance. So once we reach cache saturation, the performance does increase with the number of disks, but also the fluctuation with the number of disks, which was actually quite surprising, because one would have thought if we had more disks, that each disk would be able to operate independently, and that you do get a benefit in performance by using more disks. The possible reason for this might be a resource contention on the HBA, because as indicated, these drives are all connected to a JBOD, or being connected via a single HBA to the actual system. This HBA is running at a 6 gig SAS, or is driving a 6 gig SAS link, and obviously it's just a single HBA. So all drives have to share the bandwidth of this HBA, which means that the more disks we connect to it, the lower the combined bandwidth, the lower the individual bandwidth for each drive becomes. And this might be one of the reasons for the observed fluctuation, and also for the less than expected performance on higher disk counts. The other thing I've seen during testing was that the setup I had was quite susceptible to NUMA effects. As I've laid out earlier on, I used NV-DIMMs for the cache device. In this case, the NV-DIMM was a single namespace, which, on account of being a single namespace, was attached to one socket of the system. The whole thing, the whole system was actually a dual socket. So we had accesses to the namespace either from the socket where the namespace is attached to, but also from the other socket, which would need to go via the NUMA link to the first socket and then to the NV-DIMM. And this will lead to performance degradation when we do access the namespace from the other socket. To elaborate on this, I made a testing by using the 12 disk setup, but restricting the performance to once only CPUs on the socket being connected to the NVDIMMs and the second time to those CPUs which are running on the other CPU, on the other socket. So, and this is what you see here. With the direct access, we do get the expected performance of 2.5 gigabytes per second. But with the off NUMA access, we are only getting half of the performance, which does explain why there are so many, such a high fluctuation. And this is as the system internally also runs processes, which obviously would need to run on CPUs. So the variance you see is it might be caused by the reclaim workers, which will be started for each drive, but which are not restricted to any CPUs. So they can run on any CPU in the entire system. So it depends on the CPU, on the IO, on the scheduler, on the OS scheduler, on which CPU the reclaim workers is getting to run. If that reclaim worker is running on the on-socket CPU, then everything's fine. We get a high performance. If it's running on the off-socket CPU, the reclaim itself will have a bad performance, which then drags down the entire system. The other problem in this setup is the write application. As we have to write out data, the cache algorithm itself induces a write application. By copying out contents from sequential zones during the copy or reclaim operation, we do have to read in data and write them out to other zones. So for any modification, we will need to read in data and then write them out again, which means we actually have 1 to 3 worst case behavior. So for each IO coming in, we might need to write out the old contents, read the new contents, and write back the new contents. So this is quite a large write amplification. And here's a graph where I sketched the write amplification against the overall performance. Note here, the write amplification is just the ratio. It is not the bandwidth itself. So the ratio of incoming I/O to actual I/O being done, being driven on the disks. And as you can see here, once reclaim kicks in, we do have a quite high write amplification, which tails in neatly with the drop in performance we see on the raw disk. With 4 disks, we see an even higher write amplification. Again, what we had expected, because we do have 4 disks, so there will be a higher amplification. Again, tailing in neatly with a drop in performance. But with 6 disks, we do see that the overall amplification doesn't really go up that much. So the amplification is around a factor of 3, meaning we're having for 1 incoming I/O, we are having to do 3 I/O on all disks. And with 8 disks, we see the same behavior, that during reclaim running, meaning after around 60 tests, we do see that the write amplification is getting up, but staying at around 2, which is the reclaim worker copying data in and out. But still, the performance is pretty good, and the overall performance isn't really affected by this. But there you also see that the scalability, that the variance in performance tails in with a higher write amplification. So it's actually the write amplification which explains why there is such a high fluctuation in performance. And once the zones are used up and we run out of free zones, the write amplification goes up clearly because the reclaim has to work more aggressively, which is what we see here. But still, the reclaim, the amplification stays at around factor 3, so it's not getting higher than that, which also is a nice result. And then with 10 disks, we have the very same behavior here, that the write amplification starts when the reclaim starts, and also has some relationship to the fluctuation we see in performance, but not that a clear-cut relationship. So at around 170, you do see a drop in performance and in write amplification, which really is unexpected. And whereas at around 140, you do see a spike in write amplification, which tails in with a drop in performance. So it's less clear-cut here whether it's really the write amplification which kind of contributes to the variance in performance. And with 12 disks, we have a similar pattern again, that some drop in performance can be explained with the write amplification starting, especially the drop in performance right at the start at around 45, correlates neatly to a spike in write amplification. So that's certainly caused by that. But the next two drops in performance don't really tail in that well with a spike in the write amplification. And at around 120, we even have the inverse behavior, that we do have a drop in performance and a drop in the write amplification. So there is a quite good direct correlation between performance degradation and write amplification. This correlation becomes less noticeable if we have more disks. We have an inverse correlation between the cache utilization and the write amplification. And the reclaim really tries to run with a constant speed per disk. Higher fluctuations, we will have higher fluctuations though once it drops below the low water mark and the free zones are being used up. While these are all nice results, there is still some work to be done to explain the behavior and to make the performance even better as it is now. The one area which definitely is worth exploring is implementing DAX for metadata, because at this time metadata is handled just like normal I/O, whereas in fact it really is just a large bitmap storing the mapping table for the use blocks and also for the zone mapping itself. So it should be more efficient by implementing DAX for this one. DAX here means that it's meaning direct access, which is a feature for NVDIMM, which allows the system to map the NVDIMM directly into main memory, such that you don't need to do I/O for accessing the NVDIMM itself. This should be efficient for bitwise access, like we have for the mapping table and the bitmap table we are using to store the use blocks or to mark the use blocks. And the other big area is NUMA effects. As I've said earlier, the reclaim workers, which handle the reclaim in the current code, will be started on any CPU at this time, which means that it's not really controlled on whether the CPU is on the socket carrying the NVDIMM or whether it's running on the other socket. And we really should look at restricting these reclaim workers to run on only on-socket CPUs, therefore avoiding NUMA effects on the reclaim worker itself. Another area which needs to be looked at is how incoming I/O should be handled most efficiently. While we can control the CPUs and the work and the programs being scheduled on the CPUs, when starting a program, it's not always guaranteed that this program will run on the CPU, which is hosted on the correct socket. So one would need to look at, well, what is more efficient for these for tasks which are being started on the wrong CPU, whether it's being more efficient to use an intra CPU call to move data over, or essentially moving that particular thread over to the correct CPU, or whether it's more efficient to handle the cache bouncing and just let the system handle it. This is something which is not really clear at this time, and which needs to be investigated. And of course, there are the cache parameters which can do with some tuning. At this time, I ran with the parameters which had been there right from the start, meaning that the high watermark was about 50% and the low watermark was at 30%. So these parameters clearly would need to be investigated and it would need to be tested if and how effective these parameters are, and so one would need to do some tests to establish the best parameters there. The other area is that the cache size was being kept constant throughout all these tests, so the cache size itself has not been increased with the number of disks. But as indicated, the mapping table is also part of the cache device, such that for a larger disk or a larger disk count, we actually have less caching zones than for lower disk count, as the mapping table is eating up more space on the cache device. And so one would need to do additional testing to scale the caching size with the number of disks to see how the whole setup behaves with a larger number of cache zones. And of course, we should do tests with even more disks. At this time, I did do tests with only 12 drives. This was partially due to the fact that with 12 drives, I have seen that large fluctuation, which would need to be investigated first to reduce this fluctuation, but also partially given due to the setup I had been running with. So for the next setup, the plan is to invest into another HBA and higher speed HBA, and then connect in even more links such that we get a better performance overall and decrease the variance in performance. And of course, redundancy is completely missing at this time. This is okay for testing and for demonstrating the performance, but for real-world application, one really wants to have redundancy. It should be possible to implement a mirror-like functionality by just duplicating the setup. So essentially duplicating the cache sounds, but also duplicating the SMR sounds. The good thing here is that it should be pretty easy to implement a declustered RAID, as we do have a mapping table for the sequential access zones. So by duplicating the cache device, we will also duplicate the metadata. But as the metadata itself is already duplicated on disk, and we do end up with 4 copies of the metadata, which is actually a bit of an overkill, but it would allow us to not keep the metadata in sync. Because in the end, all we care of is that the actual data ends on both disks. Where it does end up isn't really that big of a concern, as the metadata itself is being protected such that we can reconstruct the data, or that we are guaranteed to always have a consistent view of the metadata. Such it would be possible that the metadata and that the mapping tables actually can be allowed to go out of sync, and thereby implementing some sort of declustered RAID here. Then the zone mapping doesn't need to be identical on both sides, which would be improving the reliability of the overall system, because we could easily cover up or we could easily cope with one sector failing or even entire disk failing without having to decommission the corresponding disk on the other side, which we would have to do otherwise, because if we have to keep both mapping tables similar or identical, once one disk fails, we cannot write to the same disk on the other side because the system will be degraded. Whereas it would be possible to continue to run it by just deactivating the failed disk and move the data somewhere else. So, and with that, I'm coming to the end of the session. I do thank you very much for your attention and for your patience. I will be available in the Slack channel to take additional questions and be happy to discuss the details in this presentation with you. Thank you very much.